All right, let's talk about one of the most high-stakes procedures there is, brain surgery. Today, we're diving into a technology that's basically giving surgeons a GPS to navigate the most complex terrain imaginable. Let's get into it.
I mean, just think about that for a second. It's an absolutely mind-boggling question, right? Surgeons are faced with this every single day. You've got a patient, a life, and inside their head, there's something that needs to come out. But where do you even begin in that incredibly intricate landscape?
And that is the real heart of the matter, isn't it? It's one thing to remove a tumor. It's another thing entirely to do it while protecting everything that makes that person, well, them. We're talking about their ability to move, to speak, their memories. Their entire identity is on the line. A single millimeter can make all the difference. So what's the solution? It's actually as elegant as it is powerful. Before you even think about making an incision, you create a detailed, personalized map of that person's brain, showing exactly where all the critical stuff is. So what is this incredible GPS? Well, it's a technology with a bit of a mouthful for a name, Navigated Transcranial Magnetic Stimulation, or as we'll call it, NTMS. This is the tool that lets us draw that revolutionary map. So here's the gist of it. NTMS lets doctors ping different parts of the brain, completely from the outside. A special coil is placed on the head, and it sends a super-focused magnetic pulse right through the skull. It's painless, it's safe, and it activates a tiny little patch of brain cells on the surface. And by seeing what happens, like, say, a little finger twitch, they can build that map, one point at a time. Okay, so how do they actually do this? How does the mapping process work in the real world? Well, it's a really precise procedure that has to be perfectly calibrated for every single patient. So before they can even start mapping, they have to find something called the resting motor threshold, or RMT. The analogy here is perfect. It's like finding the brain's unique volume knob. You have to find the absolute minimum power needed to get a tiny muscle response. And what's wild is that this setting is different for everybody, and it can even change for the same person on different days. Getting this right is absolutely critical for an accurate map. So once that volume knob is set, the real mapping can begin. They dial up the intensity just a tiny bit, usually to about 105%. The technician then carefully aims the coil to get the clearest possible signal. And every time a pulse makes a muscle jump, that reaction is captured by sensors. They just repeat this over and over, building this incredibly detailed point-by-point map of the brain's motor areas. But here's where it gets even cooler. NTMS isn't just for mapping movement. This same technology can be cleverly adapted to map one of our most human, most complex functions, language. And to do that, they have to completely flip the script on what they're looking for. Check out the difference here. For mapping movement, you use a single pulse, and you're looking for a reaction. You want to see a muscle twitch. Simple enough. But for language, it's the total opposite. You use a whole train of pulses, and your goal is to cause a temporary interruption. The patient will be looking at pictures and naming objects, and if the pulse hits a language center, for a split second, they can't find the word. It's a hit. You've just created a completely harmless, temporary virtual lesion that reveals a critical language hub. So cool. Now, mapping the surface of the brain is a huge leap forward, but it's really only half the story. You know, the brain isn't just a bunch of important spots. It's an incredibly dense network of connections between those spots. And this quote from the source material really hits the nail on the head. It says that protecting those deep connections, the brain's wiring, is just as important as protecting the spots on the surface. Think about it. Cutting a major highway can be just as devastating as taking out a whole city, right? And that's why NTMS doesn't work alone. It has a partner, another technology called DTI fiber tracking. And the analogy here is just perfect. If you think of NTMS as the tool that maps the functional cities on the brain's surface, DTI is the tool that maps the anatomical highways, the white matter connections that run between them. You put them together, and suddenly the surgeon has a complete roadmap showing both the destinations and the critical routes to avoid. Okay, so we've got all this amazing theory, but what does it actually mean for a patient sitting in a doctor's office? How does this map really change things? Let's look at a real case. We have a 37-year-old guy. He's got a lesion in his brain that's already messing with the coordination in his left hand. He needs surgery, but the big question for everyone is, how dangerous is this operation going to be? And this is the map they got. Those colored dots show exactly where the motor functions for his hand and leg are, sitting right up against that lesion. The colors tell you how strong the brain's response was. White is the strongest, red is the weakest. For the very first time, the surgical team can literally see the critical areas they have to protect before they even enter the operating room. So, with this map in hand, they can do an objective risk assessment. First, a bit of good news. The plan for the surgery doesn't seem to touch the motor cortex itself. That's a lowered risk. But, and this is a big but, the DTI scan shows the surgery is going to get within 8 millimeters of a major motor highway. That's an increased risk. On top of that, his initial volume knob setting was abnormal, which also points to an increased risk. And when you feed all of that data into the models, it boils down to this one incredibly precise number. This patient had a 47% chance of waking up with a new permanent weakness. That is just invaluable information. It helps the surgeons plan their approach, and maybe even more importantly, it allows them to have a really honest, data-driven conversation with the patient about the risks. And this is being used in so many other ways too. In radiotherapy, they use these maps to aim the radiation beams, avoiding critical brain areas. It's helping to objectively grade the risks for other conditions, like vascular malformations. And the map itself can actually be loaded right into the navigation system in the OR to guide the surgeon's hand in real time. But, like any technology, this GPS isn't perfect. It's an incredibly powerful tool, for sure. But it's really important to be realistic about what it can't do. At least, not yet. So first off, this doesn't replace the gold standard of mapping, which is still done during the surgery itself. It's a partner that makes that process faster and safer. Second, the magnetic field can only go so deep, so you can't map structures way down in the center of the brain. And finally, some big tumors can actually block the magnetic field, which means you just can't use it in those specific cases. So at the end of the day, NTMS gives surgeons a view of the brain that was just unimaginable a generation ago. It helps turn surgical planning from an educated guess into a data-driven strategy. That means surgeons can be more aggressive with tumors while being safer with the patient. And that leaves us with this final thought. As these maps get better and more detailed, what other conditions, not just tumors, but psychiatric and neurological issues, could we start treating with this kind of incredible precision and safety? It really feels like the journey is just beginning.